Hello everyone, I'm Chengrui Li from School of CSE, Georgia Tech. This is a short presentation of our ICML 2024 paper, a differentiable POGLM with forward-backward message passing. I will first introduce what is the POGLM problem and how to solve it using the commonly used variational inference. Then I will illustrate two issues exist in this problem and propose our solutions to them. Then I will show some experiments to compare the performance of different methods. POGLM is the abbreviation of the partially observable generalized linear model. It is a powerful tool for understanding neural connectivity, especially under the assumption of existing hidden neurons. However, POGLM itself is a difficult problem. There are two issues when using the commonly used variational inference to solve the problem. One is the gradient estimator, and the other is the sampling scheme. Okay, in the POGLM, we assume there are V visible neurons and H hidden neurons. The observed data is the visible spike train of the V visible neurons recorded from t-time bins, and the latent variable Z is the hidden spike train of the H hidden neurons from the t-time bins. The generating process is illustrated in this figure and these two equations. First, given history spikes from both visible and hidden neurons before time t, we use a linear mapping with a nonlinearity to compute the fire rates of all neurons in the current time t. Then the spike count in the current time bin is sampled from a Poisson distribution. The generative parameter theta consists the biases of all neurons and the linear weights between all neurons. If we partition them into blocked vectors and blocked matrices, we can see their corresponding roles in this iterating process. For example, W V to H is the weight from visible neurons to hidden neurons. The commonly used way of solving POGLM is variational inference. In variational inference, we need another variational model denoted by QZ given X, parameterized by phi. Similar to the generative process, it uses an encoder function to compute the variational hidden firing rates from input X, and then sample the hidden spikes from the Poisson distribution. We call them inference methods and sampling schemes. Then, in variational inference, we have this evidence lower bound. Now let's consider the first issue related to the gradient estimator. In variational inference, we need to compute the derivative of elbow with respect to phi. There are two ways of estimating this derivative. One is the score function gradient estimator, and the other is the pathwise gradient estimator. Notice that the pathwise gradient estimator only works with continuous distribution and must have a reparameterization trick. And remember that the latent variable Z represents discrete spike count from Poisson distribution. So we cannot use the pathwise gradient estimator, but can only use the score function without any modification. However, it is well known that in variational inference, the score function gradient estimator suffers from high variance issue, numerical stability issue, and so on. So our first contribution is to modify the variational model Q to make it adaptable to the pathwise gradient estimator. The relaxation consists two steps. First, we truncate the Poisson distribution at an upper bound M using this equation. Now it becomes a categorical distribution. Then we can use the Gumbel softmax reparameterization trick to approximate the categorical distribution. Now, a hard spike count becomes a soft one-hot spike count. For example, if the hard spike count is 2, then the soft one-hot spike count has a very large value that is close to 1 in index 2, and the values of all other indices are close to 0. With this soft one-hot spike count, we can also compute its equivalent spike count using this equation like an expectation. With the modified distribution, we can replace the hidden Poisson distribution in both the generative and the variational model with the proposed Gumbel softmax distribution, and then apply the pathwise gradient estimator. In fact, the differentiable POGLM we introduced before is already compatible with any single parameter continuous distributions with its corresponding reparameterization trick. So we can actually extend the distribution one step further from Gumbel softmax to distributions such as exponential, Rayleigh, half normal, and so on. Here, we plot a lot of distributions from the original Poisson to the most general continuous distributions. We list their distributions parameterized by a firing rate g and check whether pathwise gradient estimator can be used. We can see that Gumbel softmax still preserves some shape similarity to the original Poisson distributions, but other general continuous distributions do not. We will compare all these inference methods in our experiments. The second issue we want to solve is the sampling scheme, or the design of the decoder function. Existing approach assumes the posterior distribution can be approximated by a forward self process. That is, the posterior distribution can be approximated by a GLM with known x. However, this is not true, and this process is also complicated and time-consuming. We can see that to sample a sequence of z, we need a sequential sampling procedure and a recursive dependence of z back to the very beginning of the first sampled z1. This recursive dependence also introduces more noise to the gradient backpropagation. To solve it, the simplest idea is to remove the self-dependence of the hidden z. This is the forward sampling scheme. However, both the forward self and the forward schemes omit to mimic an important relationship, the hidden to visible influences. For example, if we observe a visible spike like this, it might trigger a future hidden spike, which is the decreasing probability after an observed spike event. But it might also be triggered by a previous hidden spike, which is the increasing probability before an observed spike event. To incorporate this influence, we propose the forward-backward sampling scheme, where a hidden spike is conditioned on observed spikes both before and after it. Okay, now the experiments. For a comprehensive analysis and comparison, we consider the method combinations of different inference methods times different variational sampling schemes. For Poisson, categorical, and Gumbel softmax score, we use the score function gradient estimator. For Gumbel softmax pathwise, exponential, Rayleigh, and half normal, we use the pathwise gradient estimator. The aim of introducing the two intermediate models, the categorical and the Gumbel softmax score, is to change the model step by step from the original POGLM to our proposed differentiable POGLM. The first example is a 3-visible, 2-hidden synthetic dataset. From the test log likelihood bar plot, we can see that differentiable inference methods with forward-backward sampling schemes have high likelihood and low weight error. And from the runtime, we can see that forward self is extremely slow compared to forward and forward-backward. If we plot the training curves for different method combinations, we can find that those differentiable inference methods have better convergence. Those are the sign yellow, gray, and pink, corresponding to half-normal Rayleigh exponential and Gumbel softmax pathwise. We also plot the learned linear mapping parameters and the true for reference. We can see that differentiable inference methods with forward-backward have better parameter estimation, especially in the hidden to visible block. The second experiment is about retinal ganglion neurons. In this experiment, we have 16 off cells and 11 on cells. Since we don't know how to assume the number of hidden neurons, we assume up to 3 hidden neurons. We also train a fully observed GLM, which is 0 hidden neuron, as a baseline. We can see that Gumbel softmax pathwise and half-normal with forward-backward performs better, and exponential with forward-backward performs extremely well than others, which is very interesting. To understand the significance of assuming hidden neurons, we plot the learned weight matrix. For example, we can see that in exponential times forward-backward, the learned one hidden representative neuron serves as a negative feedback regulating unit. We can use it to clearly discriminate the types of the visible neurons, whether a visible neuron is an off cell or an on cell. Finally, we try an extreme case in which we only have 3 visible neurons from primary visual cortex. In this experiment, we will assume up to 9 hidden neurons. This contains cases where the number of hidden neurons is far greater than the number of visible neurons. The likelihood results show that no matter what method combination we choose, the optimal number of hidden neurons is no more than 3. This means assuming more hidden neurons might not guarantee an improvement of the performance, but is likely to introduce redundancy and result in a dropped performance. In terms of comparison, exponential times forward-backward with less than 3 hidden neurons seems to be the best. Besides, the test likelihood variance of those differentiable inference methods is much smaller than those of the non-differentiable inference methods, due to the benefit of the pathwise gradient estimator. In summary, we propose a differentiable version of the partially observable generalized linear model, in which the pathwise gradient estimator becomes applicable when doing variational inference. The new forward-backward message passing sampling scheme is faster and more expressive. Note that the relaxation from Gumbel softmax distribution to general continuous distributions loses the meaning of C as representing spike counts, but can produce better performance. This is worth to be investigated in the future. Thanks for listening.